I'd like to introduce Simon Clarendon, who's presenting today's webinar explaining Phosphorus Buffer Index. So Simon is a researcher with the New South Wales DPI Soil and Water Unit, has a background in nutrient management, in particular the mitigation of phosphorus loss from agricultural landscapes. Simon's currently working on a variety of projects ranging from work on the south coast of New South Wales and the Clean Coastal Catchments project throughout the New South Wales Western Division in the Rangelands Living Skin project.
Thanks, Luke. So today I'd like to talk about the Phosphorus Buffering Index, what is its use and its applications. So in summary, today we will look at what is the Phosphorus Buffering Index, the history of PBI, what sits behind the PBI value of a soil, and the applications for Phosphorus Buffering Index. I would firstly like to acknowledge David Weaver and Cameron Gooley in their assistance with preparing this talk. So what is the Phosphorus Buffering Index? It is a measure of the soil's ability to retain phosphorus. So some history. How did the Phosphorus Buffering Index come about? It's long been recognised that soil characteristics strongly influence the retention of phosphorus applied, P fixation, and that fertiliser phosphorus applications needed to be adjusted accordingly. The traditional method, as up on screen, for measuring phosphorus retention has been to develop phosphorus sorption curves. These curves are developed by incubating soil at a known soil solution ratio with a range of different phosphorus concentrations. Various models, such as the Freundlich, Langmuir and Temkin models, have been used to describe these curves. However, P-sorption curves are expensive and take time to develop. Given they have 6 points of measure, it's more laboratory time in preparation, analysis time, and such become unviable in a commercial routine lab test. Therefore, researchers have always been seeking simpler methods to describe soil phosphorus retention. Some earlier methods used to estimate phosphorus retention have included the P buffering capacity, surrogate measures such as ammonium oxalate extractable iron and aluminium, and the phosphorus retention index, which was a single point measure developed for soils with lower P-sorption capacity. PBI was developed in 2002. It uses only one concentration from the P-sorption curve. It is a streamlined, repeatable, commercially viable method and is nationally applicable. In its development, we should acknowledge Lucy Burkett, who was key in developing the PBI index, and the late Phil Moody, who was also instrumental in its development and broader application. The Phosphorus Buffering Index integrates all the correlative factors that have individually been used to aid in describing or estimating phosphorus sorption previously, but have not fully explained the P-sorption capacity of a soil. To note, the PBI classification system has evolved. Initially, there were 4 to 5 classifications, but in response to new data on lower PBI soils, the classifications at the lower PBI end were further refined. There are now 9 classifications. So then, what gives a soil a particular PBI value? There are several factors that are drivers of phosphorus fixation of soils, but 2 key drivers are particle size and mineralogy. So different particle sizes will provide different surface area amounts that the phosphorus has the opportunity to attach to. Particle size is a contributor to soil texture or type. The other key driver of phosphorus fixation of soils is mineralogy. Phosphorus loves binding to iron and aluminium, and in higher pH soils, calcium. All these have a positive charge. The phosphate ion is negative. Mineralogy will influence the colour of a soil and soil type. So let's look at 2 ends of the spectrum. A grey sand with a PBI of 5 and a red clay soil of PBI 350. Picture a 1 litre container of marbles and the same size container of tennis balls. The coarser particle, being the tennis balls, has more or larger empty space in between the particles, so less opportunity for phosphorus sorption. So grey sand has a coarse particle size, it being the tennis ball relative to the clay, and has a quartz base, mineralogy, and is largely inert to phosphorus sorption. So it only has the low surface area that provides the P-sorption, hence a low PBI. Compare that to a red clay loam, which is high in iron oxides. Being a clay, it has a very large surface area, smaller particle size. It has both the larger surface area and the right mineralogy to give it a high affinity for phosphorus sorption. So it has a very high PBI. The combination of these factors will also affect moisture retention, nutrient retention, and hence pasture biomass, which will affect the stocking rates. Furthermore, the nutrient build rate and rundown rate is also affected by PBI, which we'll discuss a little bit later. Just to note, where pH lessens and aluminium becomes more available in some soils, the phosphorus will become less available as it attached to the aluminium. So how good are individual components or measures, for example soil type, in identifying the phosphorus sorption characteristics of a soil? In general terms, as we discussed, as can be seen by the red arrow, as particle size decreases and surface area increases, it contributes to an increased PBI. However, if we use soil texture, which is an individual characteristic that contributes to PBI on its own, to try and define phosphorus sorption characteristics, it wouldn't account for other P sorption factors. For example, a heavy clay may have a lower PBI than a sand, as can be seen by the two red circles, with PBI on the x-axis, or the bottom axis. The PBI measure allows us to encompass soil type, but also the other characteristics in the soil that contribute to phosphorus sorption. Similarly, in general terms, as we discussed, as can be seen by the red arrow, as you go from a grey-white soil to a red colour, it tends towards a higher PBI, as colour in part reflects mineralogy, which is a key driver of your PBI value. However, similar to soil texture, if we use colour on its own to try and define P sorption characteristics, it wouldn't account for the other P sorption factors. For example, a grey-white soil may have a higher PBI than a dark brown or orange-red soil, as seen by the red circles. The PBI measure allows us to encompass soil colour, but also the other characteristics in the soil that contribute to phosphorus sorption. So I just want to reiterate that the drivers and levers that give a soil a PBI value may change for different soils at different locations, even if they have the same PBI, but noting that the cumulative effect of these drivers gives them the same PBI. For example, soil 1 has a PBI 60 somewhere in Australia, and it may be surface area is the key driver in the sorption, whereas soil 2 somewhere else in Australia also has a PBI 60, but has mineralogy as a key driver of the phosphorus sorption. But as mentioned earlier, the cumulative effect of these drivers gives both soils the same PBI. So how is PBI measured? Briefly, it is a single addition of P to our soil sample at a 10:1 ratio and shaken for 16 hours. So 100 milligrams of P per litre in solution and 1,000 milligrams of P dosed to the soil. To explain further, on the left axis, we have the amount of P sorbed to the soil. On the bottom axis, we have the equilibrium phosphorus concentration, which is the point that no P is absorbed or desorbed. If no P is absorbed, the 100 milligrams of phosphorus per litre remains in solution. If all the P is absorbed by the soil, 0 milligrams of phosphorus per litre remains in solution and 1,000 milligrams of P per kilogram is retained by the soil. There are two forms of PBI, adjusted and unadjusted. Unadjusted PBI tracks the current capacity of the soil to retain phosphorus, while the adjusted PBI aims to report the phosphorus retention capacity of the soil in its virgin or unfertilised state. When Colwell P is very low or close to 0, adjusted and unadjusted PBI are the same, as we can see up on the screen with the 1, 20 and 0 Colwell P. As the soil P fertility increases, unadjusted PBI decreases, reflecting a decrease in the current capacity of the soil to retain phosphorus, while adjusted PBI, which accounts for Colwell P in the soil, remains the same. Adjusted PBI is useful for agronomic measures. It allows the identification of the inherent characteristics we earlier discussed that drive P sorption, for example, the iron and aluminium oxides. This allows the provision of an appropriate soil test critical value for production for a soil with a certain PBI. Adjusted PBI is the standard method used in labs. As unadjusted PBI tracks the current capacity of the soil to retain phosphorus, we can utilise PBI unadjusted to track the soil's diminishing capacity to retain phosphorus with continual additions of phosphorus. So it can be a potential identifier of environmental risk. So how can PBI be utilised? It can be utilised in multiple ways, and I want to touch on these as there has been confusion for some of the applications of PBI. First of all, we can use PBI for fertiliser applications, adjusted according to the PBI of soils, and the Phosphorus Environmental Risk Index, otherwise known as PERI. As we have discussed, soils have different abilities to hold on to phosphorus. The aim of this slide is to highlight the difference in the PBI of the soils that affects the Colwell P soil test critical value. Colwell P measures the plant available phosphorus in soils and is the dominant soil test used to measure this. Historically, the interpretation of soil test Colwell P results, and hence the applications of fertiliser, was a one-size-fits-all or based on one soil characteristic that contributes to P sorption. However, PBI gave us the changes in critical values that adjust to the P sorption characteristics of different soils. So let's have a closer look at how PBI affects critical soil test values. On the left axis, we have the relative yield or percentage of maximum production. And on the bottom, on the x-axis at the bottom, we have the Colwell P soil test value. In this example, we used extremes end of the PBI classifications. So a soil with a very low PBI, most likely a coastal sand. In this example, if we follow the 95% of maximum production yield and follow from the left axis across till we hit the curve for the soil with a very low PBI, the dashed line, then go directly down, we see a soil with a PBI of about 5 requires a soil test Colwell P value of 10 to reach 95% of maximum production, whereas a soil with a high PBI, such as 560, requires a Colwell P soil test of 55 to reach 95% of maximum production. Where above these values, there'll be no response to further application of P, and under these values will provide a plant production deficit, assuming all other nutrients are not limiting production. In summary, PBI affects the soil test critical value for target production. As we can see, it takes different amounts of phosphorus to reach the critical P levels for different PBI soils. The rundown time of P is also affected by the PBI. As higher PBI soils take a longer time to build up their soil test P values, so it does to run down their soil test P values than the lower PBI soils. So we can further look at how PBI and Colwell P go hand in hand. Through over 3,000 plus of trial years, otherwise known as better fertiliser decisions for pastures, we now have the critical soil test values for Colwell P. So for each PBI, we have a different Colwell phosphorus soil test critical value. The examples I'm about to present are based on 95% of maximum production for pastures, largely dairy. Less intense grazing farms may have lower relative yield targets depending on how hard the system is being pushed. Given that different soils have different PBIs, the soil test critical values will change. A low PBI soil, which doesn't have the capacity to hold on to phosphorus, will have a low critical value. As PBI increases, the critical soil test Colwell P value required for plant production increases. To reiterate this, we have made some soil tests up. So soil test A is on a very low PBI soil, or extremely low. The Colwell P soil test value is right on the critical value for that PBI. If we look at a higher PBI on a soil test B, it is also right on its critical value for plant production, that being the Colwell P value. So note, just wanting to make clear and note that for higher PBI soils, the critical value is higher. So let's look at more soil tests that have the same PBI but different Colwell P values. Soil test D with a PBI of 100 is below the critical value for 95% relative yield, which is a value of 33 as seen on the left. So there is a need to apply phosphorus. If we look at soil test C, it is above the critical value for P, so over double for the same PBI soil, so there is no need to apply phosphorus. PBI is a regulator for the change in critical soil test values for Colwell P. They go hand in hand. I'd also like to note that for some other tests used, such as Olsen P and Bray P, they have smaller extraction times to that of Colwell P, and PBI is not needed to make adjustments, but PBI is used when adding P to soil for capital applications for Olsen P. So I've put up a QR code which will take you to a nutrient calculator for pastures. This allows you to input your P, K and S and pH soil test values to ascertain if you have enough phosphorus, potassium and sulphur and a suitable pH for the relative yield you are chasing. So to start discussing what else PBI can be used for, I thought it'd be good to put up a farm map of PBI that shows that on a farm, PBIs can be highly variable. This in turn, with assessing the phosphorus fertility of paddocks, per Colwell P against soil test critical values, can assist us in identifying the areas of high risk of P loss. So how can we do this? PERI, or Phosphorus Environmental Risk Index, is a P loss risk indicator using agronomic soil measures. It provides insight into a soil's degree of phosphorus saturation and the likelihood that soluble P may be lost from the topsoil, be it leaching or desorption from the soil surface. PERI is the Colwell P soil test value divided by the PBI of a soil. As your Colwell P increases, or your PBI decreases, or both for a soil of a particular PBI, so will your risk of loss increase. Using some real soil test results, let's have a look at a risk of two PBIs, a medium PBI and a very high PBI. Soil 1 has a PBI of 62 and a Colwell P of 47, so it has a PERI value was 0.75. Soil 2 has a PBI of 400, so it has a higher capacity to retain P. However, it had previously been used as an effluent spreading paddock on a dairy, so it had a Colwell of 300. That is 5.5 more times than the critical value for plant production at 95% relative yield. As you can see, both soils have vastly different PBIs, but they have the same risk of loss. If we change those values of Colwell P for the two soils to the critical value required for 95% relative yield plant production on a soil with a PBI of 400, the risk increases for the lower PBI soil, remembering that the critical value for that PBI soil is lower, and reduces for the higher PBI soil. So I just want to clarify that obviously there is that need for different critical values for different PBI soils. If we want to specifically target looking at potential losses that aren't from leaching, for example, surface runoff from a high PBI soil, we can do incremental soil depth testing. In this case, we did a 0 to 10 centimetre sample, as well as a 0 to 1 centimetre, 1 to 2 centimetre, 2 to 5 centimetre, and 5 to 10 centimetre sample at the same site. As can be seen by the red dot, which is the 0 to 10 centimetres PERI value of about 0.7, but if we take that 0 to 1 centimetre sample at the surface, the PERI is almost double, indicating higher saturation of P at the soil surface and more risk of loss from desorption or erosion. While PERI is a fantastic measure, understanding the risk of P loss, we should consider other things such as slope, proximity to watercourses, bare ground, surface cover, fertiliser timing, stocking rates, amongst other things. To further highlight the influence of PBI on assessing the risk of phosphorus loss, I'd like to present a schematic. Colwell P measures the P available to plants. A portion of that measured Colwell P is readily available in solution or highly soluble. A good measure of this is calcium chloride extracted phosphorus. The portion that is in solution will vary, with more or less of the plant available P will be in solution. When I'm discussing this, calcium chloride extractable P can be interchangeably described as soil solution phosphorus or soluble P. So how does PBI affect this ratio? In recent research, Weaver et al. 2023 showed that the benchmark measure of soluble P loss risk, that being calcium chloride extractable P, was positively correlated to Colwell P when the data was differentiated by PBI. So the chart on the left, we can see the different lines is different PBIs. The left axis has the amount of calcium chloride extractable P measured, and on the bottom axis has the amount of Colwell P measured. As we can see the lines for different PBIs, that the soluble P loss increases as Colwell P increased for all PBI soils. However, the proportion of Colwell P measured as soluble P was affected by PBI, with lower PBIs having the portion of plant available P more in solution. To try and untangle that chart a bit more and simplify it, we can plot the slopes of these PBI delineated relationships of calcium chloride extractable P and Colwell P, as the slopes indicates the proportion of Colwell P that can be measured as calcium chloride extractable P or as a soluble P. So the slopes of these relationships decreased as PBI increased. So what does that mean? So for very low PBI soils, less than 5, almost all of the Colwell P was measured as calcium chloride extractable P. While once we went for soils above a PBI of 100, around 5% of the Colwell P was measured as soluble P. This shows that the risk of soluble phosphorus loss increases rapidly as PBI decreases below 100. And this can be seen by the rapid increase upward of that curve, or the points, as you look at a PBI below 100. So I just wanted to highlight some technologies that may further reduce the time on measuring PBI and done in field. Work has been done looking at both the mid-infrared spectroscopy, handheld, and the portable X-ray fluorescence. There's potential to get in-field measures for PBI, which would mean minimal preparation and effectively stand and scan in the paddock. So in summing up, I've tried to explain some of the key drivers of phosphorus sorption that determine the PBI value of a soil, and that the PBI integrates all of the drivers of P sorption and is a nationally applicable test. PBI is not only a measure, but a tool and has multiple uses, both agronomically and environmentally. Colwell phosphorus measures needs to PBI to determine the appropriate critical soil test values for production that is being targeted. But also PBI, along with multiple other soil test measures such as Colwell P and calcium chloride extractable P, and the soil test critical values can be used to assist in determining the risk of phosphorus from the farm landscape. And that's it. Thanks, Lou.